So let's do part 2. How much bigger is the sun than the earth, and why am I doing this? Well, last episode you saw these numbers, and these numbers I'll sit here and claim to be, this is by how many factors larger the sun is than the earth. Well, which one is it? See, this is why context is important, and you don't use vague words like bigger and larger and stuff like that, because even though as small children we can discern which glass of water has more or the same just based on the volume of the container, stuff like this, we need to be better than that. We need to be more clear about what we are saying. You are going to see me do some equations on the board here, and I bought this today, I've started keeping track of my equations and stuff for videos only in here. Pictures from this on the inside will be at the very end of the last video, just so you know my actual calculations, and you may even catch some errors I made. Okay, so we have all these numbers, and just for future reference, this is the first time, this is for like 100 times. You may have seen that written a lot, but I don't want to confuse that with the multiplication symbol and the equations. So you're going to see when I start talking about 100 times later on, you're going to see this dropped for F. And that doesn't mean force, it means factor. And if it's a factor of density, I'll have the density symbol. If it's a factor of the sun only, I'll have this a little S or a little E if it's just for Earth, etc., etc. But every one of these is basically correct. Well, but which one's most realistic? Well, like I said in the first video, we live essentially in a universe with 3 dimensions of space: length, width, and height. Everything around you has it. Even a piece of paper. You know, we sit there and we draw on it, and we say it's 2-dimensional, but this is a 3-dimensional object. It has a thickness or height to it. There are no 2-dimensional objects, or 1-dimensional, or 4-dimensional spatial objects in our universe that we're aware of. This right here is perhaps the most common thing I've seen written, and is the most inaccurate. When we say the sun is 100 times larger than the earth, that is a 1-dimensional claim. We are using the diameter. What that means is it takes 100 Earths side by side to equal the diameter. It's actually a little more, we'll go through it, to equal the diameter of the sun. Well, the sun has no solid surface. I just need to say this really quick. We consider its photosphere the surface, the part we can see, and we can measure that. All right, this one here and this one here are the most common, and they are based off 3 dimensions. But there's 2. We'll come back to that. And this is the most least common. This is based off 2 dimensions. This would be the disk, how it appears in the sky. The sun appears to us as a disk because it's fully illuminated. And if you've used filters like I have to look at it, it looks like a disk. Well, if we took the Earth, say we were standing somewhere in space and we were fine, and put it right next to the sun, we would also just see a disk. The further you look into the distance, the less 3-dimensional your vision becomes. And so it would look 2-dimensional. So it would be the disk of the sun next to the disk of the earth. The apparent surface area of the sun is 12,000 times that of the earth. What are these? These are our 3Ds, okay? This one is mass, and this one is volume. So if someone says the sun is 300,000 times bigger than the earth, they are talking about mass. If they say the sun is 1 million times bigger than the earth, they are talking about its volume. Now, I need to say something here about mass and volume. They are generally intrinsic properties of solids. They don't change. Mass is the amount of stuff you can push into an area, and that will give you a certain density, if you will. The volume is just the amount of space, that length times width times height, that object takes up. Last episode we put this on a scale and we got 100 grams. This is also the same. It's made of the same material. Volumetrically, they take up the same amount of space. But what if this one was 200 grams, but it had the same circumference, radius, diameter, everything else that this one has? Well, the volumes are the same, but this one would be twice as massive. It has 2 times the mass, even though they are volumetrically the same size. So that's where these two numbers come from, and that's why this one is lower than this one, because you can put a lot of Earths into the sun volumetrically, but the Earth's average density, and we'll come back to this, is a lot larger than the sun's, because the sun is basically a big ball of gas, as where the Earth is generally solid and liquids. Granted, the density of the sun isn't consistent throughout. The density is an average density that you're going to see. Same thing with the Earth. The density of the Earth is not the same throughout. So I'm going to show you, I'm going to walk you through these. Let's go from 1 dimensions to 2 to 3 to show you how this works. We'll start with 1 dimension. And we're going to talk about diameter. That's what this capital D means. And R is going to be our radius. I probably should have written that there, equals radius. And you're going to see that throughout. But here we have a radius of the Earth and a radius of the sun. Now, how do we get the diameter? Well, radius is half the diameter. So you just multiply by 2. This is going to be the simplest of all of these problems in this episode because it's one-dimensional. But to get our diameter of our sun, we take our solar radius, multiply it by 2, we get 1,392,690 kilometers. We do the same thing for Earth. We take its radius, multiply it by 2, we get 12,742 kilometers. Now, what do we do with this? Well, in order to get the ratio or the factor of how much, we're going to keep it simple here, okay? As much as I can. We need to divide the larger by the smaller. So we're going to do that here. We are going to divide this by this, okay? And these will cancel because we're getting a factor, a ratio. After we cancel this and do some rounding, we get 109. What does that mean? That means the sun is 109 times the diameter of the Earth. So if you put 109 Earths side by side along the sun's equator and just held them up there, it would take 109 of them about to go across. That's where that 100 came from. Some people simplify it even further. Actually, this number from this calculation has a bunch of other stuff after it we don't care about. Okay? That's a decimal. And we are just going to call this number our F. We're just going to call this 109F. It's our factor. Like I said, I don't want to use X's to confuse you with multiplication. And that's where that comes from, okay? And that's just 1 dimension. You shouldn't be using this at all. We don't live in a 1-dimensional or even a 2-dimensional universe where you can apply this to some extent. People shouldn't do this. They shouldn't say the sun is 109 times bigger or 100 times bigger than the Earth. It doesn't mean anything. It's in any context, all right? It doesn't mean anything. Just real quick on that, on the diameter thing, 109, you could have divided the radiuses by one another and gotten the same number. I just did the diameters to give you the concept of what people are actually doing, all right? So I just didn't want to confuse you there, but note, some of you may notice that you can use radius as well. We aren't going to spend too much time on the area because that number isn't the one you see most often. Actually, that 100 is probably the most, followed by the 3D ones. But it does appear. So when we're talking about 2D here, we're talking about, in this case, well, the Earth and the sun are being modeled as perfect spheres. I know they're not. Well, the sun might be, actually. But whatever, okay? For our purposes, it's fine to model them as perfect spheres. a sphere is a three-dimensional object. In 2 dimensions, a sphere is a circle. And that's what we're going to do here, is figure out our area of a circle. And in 1 dimension, any shape is a line segment, because 1 dimension is a line. So in order to calculate our area, here you're going to see pi a lot here. And this, you're only going to see this once. So this is the number. That's how many decimal places I took it to when calculating in each and every one of these. Just so you know, I just don't want to have to write it and clutter up the board each and every time. So in order to figure out our solar area, we multiply the square of our radius of the sun by pi, and we get this erroneously large factor. Hold, stop. I inadvertently wrote F up here when I should have written kilometers squared. I apologize. The F only belongs in the very final answer of about 1.523 billion with a B. Earth's area is a little more manageable at about 127,516,000. Okay. So what do we do with this? What factor do we come up with out of that? Well, you already know the answer, but I'm going to show you how we get it. That's the point of this. Well, we do the same thing we did last time. See, the great thing about, you can deal with all this. If you want to use all this stuff, you can, to figure out how many times larger, whether it's 1, 2, or 3 dimensional you're doing. But it's easier to convert it to factors and then deal with these. Because even though these numbers can be big, they're less of a hassle than these and less prone to error than lengthy equations. And that's all we have to do most of the time to get our factor. Actually, every time, is we just divide the bigger into the smaller. Okay? And we're going to do approximations here. I mean, you can see how many decimals I dragged it out to in the end at the notes. But we do this, and now if you want to handle the numbers here, I'm not going to use scientific notation, all right? And some of you might be pulling your hair out, but I need you to see these numbers written. And we get to 3D, they're going to be even worse, okay? So, but we can divide this in our calculator by doing something. We have 3 zeros here in our ones, tens, and hundreds, and we do here as well. We can actually drop these in our division. So when we enter our calculator, we would just be entering 1,523,000 divided by 127,516. We get the same number as if we had these zeros. That's why using factors helps a lot more. And we come up with about a factor of 11,900. That's where that 12,000 comes from. So if you see the sun is 12,000 times or 11,900 times larger than the Earth, it has to do with the disks in 2 dimensions. Okay, so ignore this for now. Don't panic. We're dealing with 3 dimensions and volume first. I'm doing volume first because I'm going to do mass in 2 ways, but we need the volume from this one in order to do it. The mass will be the longest segment. But the volume of a sphere, because now I'm dealing with 3 dimensions, is 4/3 pi r cubed, or 4.18879 radius cubed. R is radius, always, sorry. I just wanted you to see that because I got this from multiplying 3.14, whatever the rest of the pi was, times this, which is 1.3 repeating. I carried it to 5 decimal places. I just didn't want you to be like, where'd this number come from? This number is that number, which is 4/3 times pi. And remember, it's multiplication. We can multiply in any order we wish. So first I need to figure out my solar volume. So I take my 4/3 pi r cubed, and I don't even know what this number would be called. It's 1.4 about times 10 to the 18th. I think that's right. That's 10 to the 18th power in scientific notation. All right. Let's just leave that there. That's a big number we get. I just wanted to show you how much larger the numbers become every time you add a dimension of space. So our Earth volume, same thing, radius cubed. And this number I can tell you, 1,083,203,000,000 cubic kilometers, about, I rounded. How do we get our F, our factor? Well, do the same thing we did last time. We just divide these two because they are essentially factors, of one another. I mean, they got the same units and everything, which are going to cancel immediately. And I can do the same thing I did before. But this time, I'm going to take it to 6 zeros when I divide. Now, I'm doing this because a phone calculator can handle these numbers pretty easily without scientific notation. I'm assuming you don't have a graphic calculator, because if you did, this stuff is probably very simple to you, but I could be wrong. So we divide those two together here, and we divide these two, get rid of our units to get our factor, and we get about 1,306,000. What does that mean? Well, that means I can fit volumetrically. Okay? If I took the volume of the sun and cut it into 1,306,000 pieces of equal size, I would have each piece being the same volume as one Earth. Okay? Because the sun is 1,306,000 times the volume of the Earth, which is where that 1 million came from that I showed you in the last video in the beginning of this one. 1 million is just rounding this even more. This, to me, if you're talking about bigger, just size-wise, how much larger is something compared to something else? Because if I just show you, I have these two here side by side, and just by looking at them, you don't know which one is more massive. Now, I've already told you they have the same mass and the same volume, but if you didn't know, volumetrically, you could say they're the same size, and that's logical just by looking at something, giving it a go with the eye. So volume makes more sense. Now, if we were to do fourth Doctor TARDIS logic here, it'd be, oh man, I wish I had a smaller one. Oh, I could use any object, really. So volume, to me, is the most logical one to use when talking in lay speak. But when you're talking in science, people are generally going to refer to mass of things, the relative mass to something else. Okay, so 3D mass. This is going to be our raw mass. We're going to use the mass of each body to get our factor here. Now, I said I wasn't going to use scientific notation, but I'm showing it to you here because I'm not writing all these zeros out. This is just too many, and that's in kilograms. I could have done it in, I guess, metric tons or something, but it really wouldn't have shrunk these numbers that much. But this is basically 5912 with 21 zeros after it. This is essentially 1989 with 27 zeros after it. So this is far larger than this, and you can tell by the exponent. The bigger number is always going to be the bigger object when talking about mass in this particular case. So I just wanted to do that because I'm going to do something to those to get my factor. Now, I'm not going to show the maths on this, all right? But if I divide this into this, I'm doing the smaller one into the larger one, and there's a method to my madness here. What I'm going to get if I divide these two is I'm going to get a factor of 0.0000303, and I have this in solar. Now, what does that mean? That just means the Earth is that small of a fraction compared to one of the sun. All right, I didn't do the larger and the lower like I've been doing because I need this number. And I'm calling it solar factor instead of Earth factor. All right, because I need to do something with this. It was basically to get rid of those lengthy scientific notations is what it was. So when I set this up, I'm going to divide my one solar factor, which is one sun, and my fraction of a solar factor that my Earth is. I could have just divided this by this, put this on top of the division in the numerator instead of the denominator, and got this number. You can solve things different ways, and you may see this again where it has to be done this way, okay? But anyways, we do that, and we get 330,000 for our factor because technically these are going to cancel, but we still have our factor. So this is how many Earths it would take to equal one solar mass, because we're talking about one solar mass, okay? Because we're dealing with mass here. So it would take 330,000 Earths to equal one solar mass. Wow, why is that? Why is this number so much less than that volume number? We're still using 3 dimensions of space. That hasn't changed. Well, it has to do back with that first episode I showed you when I went on that rant about density, when I showed you the ball and the rock. The Earth has a greater density than the Sun by far, and I'm going to recalculate mass using density, and we'll see how close of a number we get. But when we do our comparison, we're going to use less rounded numbers, so be prepared for that. They're not going to match exactly what you've seen already. So let's get into that part. Now, after seeing the just straight mass based off the actual masses in kilograms of the previous part I just ran with you with that huge scientific notation, you may be wondering, Steve, is there an easier way to calculate the factor mass difference? There actually is, using the average. When I say average, I mean mean average density of both. And I'm not even going to take it to too many decimal places. I don't need to. And you're going to see it's really close to that 303,000 that we just saw. But we got to go through it here. So we're going to use density here instead of the actual mass in kilograms. So we divide our two, these cancel, and what we end up getting is 3.90780, which is equal to our factor density in this case. Right, so we're going to be working with this number now. As you can see, what this tells us is the Earth on average, for what that's worth, is about 3.9 times more dense than the Sun. And that makes sense, even though the Sun is so much larger and so much more massive, and at its core, its density is far denser than anything we have on Earth, but it's in that gaseous state. And Earth is not in a gaseous state. The only gas is our atmosphere. It's the inner core is solid. All right, so we have heavier elements making up the vast majority of Earth, as where the Sun is mostly hydrogen and helium. All right, so we're going to get into density here. Density is mass over volume. You've already seen this in the sandstone block episode I did right before this one, so I'm not going to go too much into detail, but the same thing there. We need a mass. Our mass is unknown, so what we're going to do is you need to do something to both sides of the equation to get stuff to cancel out. What you do to one side, you have to do to the other. So we multiply it by volume here. These cancel. We multiply by volume here. So what we end up with, our mass is equal to our density multiplied by our volume, just like it was in the sandstone block episode that I did before this three-parter. So we had F density, our factor density, and before I erased it there, we had this. We're going to set that to our Sun instead of Earth, because I want to show you something here. So our density and our volume to get our mass is we have our volume times our density. This is our volume. This is a more drawn out version of our volume that we calculated earlier. Now we have to multiply that by our density. But we have our density factor, which was that 3.90780. But we don't just multiply this by this, because this is our volume. How many Earths will fit into the Sun? So this is in Earth volumes. So I need to be consistent. So we aren't just going to multiply this by this. This is how many Earths it would take to equal the volume of one Sun. So I have to keep my units consistent. I have to use the Sun. That's why I'm going to use a solar factor here. And if I was to use the Earth factor, and if this was Earth's, then I would multiply straight away. But I can't do that. Well, I can, but I just need to show you. I'm going to essentially divide, but I want to show you how you convert this factor to the solar factor that I need. our density factor here, I cannot multiply straight by this. I need to convert it into that solar factor that I mentioned. Why? Because this is how many Earths, volumetrically, it would take to fit into the sun. I'm doing sun to Earth, so I need to convert something. I'm still going to multiply, but I can't just multiply straight away. I need to flip this. So I multiply by 1 divided by our density factor. This is in parentheses. I do this first. Now, I do this. I don't need to divide this by this and multiply it by this, because this is also a fraction, if you remember from my sandstone block episode. There's a 1 under that. These cancel. So we just reposition everything, okay, like this, simplifying it. We divide this out, and we get about 334,000. What's that mean? Well, that's how many Earths via mass it would take to equal the mass of one sun. That's really close to what we just did right before this. So I can calculate the relative masses using density or using the actual masses themselves to get this number. That makes sense? I hope so. So you see, you can use that average density to get how many Earths will fit into the sun. And you can see we're not that far off. Okay, so to wrap this up here, you can see the importance of context in saying something is bigger than something else. You know, just saying it's larger isn't necessarily satisfactory. And these are what we just went through. And, you know, these numbers vary wildly. None of them are even close. It depends on the dimension that you're using. Because remember, 1D, anything in one dimension, is a line. And I'm going to try to represent 3 dimensions on 2 here. So that would be a line segment, and that, or your x-axis in a plane. And your 2D, you're adding this component, the y-axis in your plane. And in the 3D, your z-axis. Now, can we have done density for a 2-dimensional thing as well? Sure, we could have, but no one's going to do that because we don't live in a 2-dimensional universe. And I would have to use that 3.9 and some change, that cricket's going, to calculate it. It's not worth it. I've never seen it. I've only seen the 2D as the surface area of a sphere. I've only seen the 2D as a surface area of a circle. Here's your 1-dimensional sphere. Okay? Here's your 2-dimensional sphere. It's a circle. My sloppy drawing there. And here's your 3-dimensional sphere. It's a sphere. 4th dimension would be a hypersphere. I think there's another name for it too, but I don't know. So context is important. And like I said, for the average, just saying, you know, the sun is bigger than the earth, in a lay speak, this is the one you want to use. You want to use volume. You never want to use these ever. They're worthless. Well, this one has some uses, but this is completely worthless on any scale. And if you're hearing scientists more often, we like to compare mass to mass. If you didn't just sit through these lectures with me and watch me calculate these masses and areas and whatnot, and you heard me say the sun is 3,330,000 times larger than the earth, but you heard some guy say it's 109 times larger, you'd be like, what? Well, that's why I wanted to show you all this. But anyway, I think that's it before this drags out anymore. If you have any questions or comments, please leave them below. I hope you learned something. Remember, we have one more episode.